Welcome to today's session. We'll be tackling LeetCode problem number 1913, maximum product difference between two pairs. This problem challenges us to identify the maximum product difference between two pairs of integers from a given array. Stick around as we break it down step by step. In this problem, we're tasked with finding the maximum product difference between two pairs of numbers in an array. Specifically, you're given an array called nums that contains an even number of integers. From this array, you need to select four distinct indices, I, j, k, and l. The goal is to maximize the product of the two largest numbers while simultaneously minimizing the product of the two smallest numbers. Once you calculate these two products, the maximum product difference is simply the difference between the two, the product of the largest numbers minus the product of the smallest numbers. This is the value you need to return as the output. The constraints ensure that the array length is even, and every element in the array falls within the range of 1 to 10,000. The output for this problem is a single integer that represents the maximum product difference. To help understand this better, let's look at an example. Suppose the input array is nums equals 5, 6, 2, 7, 4. The two largest numbers in this array are 7 and 6, so their product is 7 * 6 equals 42. Meanwhile, the two smallest numbers are 2 and 4, and their product is 2 * 4 equals 8. To find the maximum product difference, we subtract the smaller product from the larger one, 42 8 equals 34. Therefore, the output for this input is 34. Now let's consider another example to further clarify. If the input is nums equals 4, 2, 5, 9, 7, 4, 8, the two largest numbers are 9 and 8, giving a product of 9 * 8 equals 72. The two smallest numbers are 2 and 4, with a product of 2 * 4 equals 8. Subtracting the smaller product from the larger one gives us 72 8 equals 64, which is the maximum product difference. Thus, the output for this input is 64. These examples illustrate how the problem is solved step by step, starting with identifying the largest and smallest numbers, calculating their products, and then finding the difference. This problem also includes some constraints and edge cases to consider. First, the array length will always be even, ranging from 2 to 10,000, and all elements in the array will be between 1 and 10,000. For edge cases, think about scenarios like the smallest possible array size, such as nums equals 1, 2, 3, 4, where the result is straightforward. If all elements in the array are identical, like nums equals 5, 5, 5, 5, the maximum product difference will always be 0 because the largest and smallest products are equal. For larger arrays with up to 10,000 elements, it's important to ensure the solution is efficient and handles the computation within the time limits. Additionally, arrays with a wide range of values, such as numbers spanning from 1 to 10,000, should also be tested to confirm the correctness of the solution. To solve this problem, we need to compute the maximum product difference between two pairs of integers in the array. Specifically, we calculate the difference between the product of the two largest numbers and the product of the two smallest numbers. This means identifying the largest two numbers, which we'll call maximum_1 and maximum_2, as well as the smallest two numbers, minimum_1 and minimum_2, from the array. Now, a key observation here is that sorting the array directly gives us these values, with the smallest numbers at the start and the largest numbers at the end. However, instead of fully sorting, we could also use an optimized linear time approach to find the two largest and two smallest numbers without sorting the entire array. Importantly, since only the largest and smallest values are relevant, the rest of the numbers in the array can be ignored entirely when forming these critical pairs. One approach we could take is a brute force method. This involves generating all possible pairs of indices, I, j, and k, l, in the array, where the pairs are distinct, and then calculating the product difference for each combination. While this guarantees correctness, it is highly inefficient. The time complexity is O(n), due to the 4 nested loops required to generate all pair combinations, which makes it unfeasible for larger arrays, especially as the input size can go up to 10. On the other hand, a much better approach is to sort the array first. By sorting, we can directly pick the two smallest numbers from the beginning of the sorted array and the two largest numbers from the end. The product difference can then be calculated using just these 4 values. Sorting has a time complexity of O(n) log n, and is space efficient if done in place, making it a significant improvement over brute force. Sorting is simple to implement and ensures correctness, but it isn't the most efficient solution for this problem. A more optimal approach is to perform a single linear scan of the array to identify the two largest and two smallest numbers. This method eliminates the need for sorting entirely. To implement this, we initialize variables for the largest and smallest numbers, max1, max2, min1, and min2. We then traverse the array once, updating these values as needed whenever we encounter a number larger or smaller than our current maximums or minimums. Once the scan is complete, we can calculate the product difference in constant time using these four values. This approach has a time complexity of O(n), as it requires only one pass through the array, and a space complexity of O(1), as no extra data structures are used. While slightly more complex to implement than sorting, it is significantly faster for large inputs. Given the options, the optimized linear scan approach is the best solution due to its efficiency and minimal memory usage. Sorting, while simpler, is slower with its O(n) log n complexity, which is unnecessary when we only need 4 values from the array. The brute force method, on the other hand, is completely impractical due to its exponential runtime, making it suitable only for small test cases or edge case analysis. In summary, the brute force approach is too slow, sorting is easy but not optimal, and the linear scan strikes the ideal balance between speed and memory efficiency. This makes the linear scan approach the most appropriate choice for solving this problem, enabling us to handle even the largest input sizes efficiently. To solve this problem, our goal is to compute the maximum product difference between two pairs of integers in the array. First, we need to identify the two largest numbers, which we'll call maximum_1 and maximum_2, and the two smallest numbers, minimum_1 and minimum_2. Using these values, the formula for the result will be the product of the two largest numbers minus the product of the two smallest numbers. Since the problem guarantees that the array has at least 4 integers, we can focus on efficiency. Instead of sorting the entire array, which would take O(n) log n time, we can use a linear pass to find the top two maximums and minimums in O(n) time. This method is faster and avoids unnecessary computations, making it the optimal choice for this task. Now, let's break down the algorithm step by step. We start by initializing 4 variables to track the two largest and two smallest numbers. Specifically, max_1 and max_2 will store the two largest numbers, while min_1 and min_2 will store the two smallest. Initially, max_1 and max_2 are set to -infinity because we're looking for the largest values, and min_1 and min_2 are set to +infinity because we're looking for the smallest values. As we traverse the array, we'll compare each number to update these variables. Once the traversal is complete, we use the formula to compute the product difference, which is max_1 asterisk max_2, min_1 asterisk min_2. Finally, we return this result as the output. During the single pass through the array, we process each number to determine if it updates the maximums or minimums. For the maximums, if the number is greater than max_1, we shift max_1 down to max_2 and assign the new number to max_1. If the number is not larger than max_1 but is greater than max_2, we update max_2. Similarly, for the minimums, if the number is smaller than min_1, we shift min_1 down to min_2 and assign the new number to min_1. If it's not smaller than min_1 but is smaller than min_2, we update min_2. After finishing the loop, we calculate the product difference using the formula max_1 asterisk max_2, min_1 asterisk min_2. This final value is then returned as the result. To understand why this approach works, let's consider some key insights. Using a linear traversal is more efficient than sorting because it allows us to find the required values in O(n) time, as opposed to O(n) log n for sorting. Maintaining 2 maximums and 2 minimums is necessary because the product difference depends on both the largest and smallest pairs. If we tracked only one maximum or one minimum, we wouldn't have enough information to compute the result. The algorithm also handles edge cases well. For example, when the array contains exactly 4 elements, all 4 are processed correctly. If all numbers are the same, the product difference will naturally be 0, and the algorithm accounts for large input sizes efficiently due to its linear complexity. From a data structure perspective, this algorithm is highly efficient. We only use for scalar variables, max_1, max_2, min_1, and min_2, to store the intermediate results. This ensures that the space complexity remains constant at O(1), regardless of the input size. The array is traversed in a single pass, leading to a time complexity of O(n). This combination of linear time and constant space makes the algorithm well-suited for handling large arrays. By focusing on simplicity and efficiency, we avoid unnecessary overhead while still solving the problem optimally. Let's walk through an example to see how the algorithm works in practice. Consider the input array nums equals 4, 2, 5, 9, 7, 4, 8. We start by initializing max_1 and max_2 to negative infinity, and min_1 and min_2 to positive infinity. During the first pass, we process each number one by one. For the first number, 4, we update max_1 to 4 and min_1 to 4. For the second number, 2, we update min_2 to 2. When we encounter 5, max_1 becomes 5 and max_2 becomes 4. For 9, max_1 is updated to 9 and max_2 to 5. The next numbers, 7 and 4, don't change the maximums or minimums. Finally, 8 updates max_2 to 8. At the end of the pass, we have max_1 equals 9, max_2 equals 8, min_1 equals 2, and min_2 equals 4. Now that we have the values, we can calculate the result. Using the formula, the product of the two largest numbers is 9 multiplied by 8, which equals 72. The product of the two smallest numbers is 2 multiplied by 4, which equals 8. Subtracting these values gives us the product difference, 72 minus 8 equals 64. Therefore, the output of the algorithm for this input is 64. This example illustrates how the algorithm efficiently processes the array to find the maximum product difference in a straightforward manner. This Python implementation solves LeetCode problem number 1913, maximum product difference between two pairs. The goal is to calculate the maximum product difference between two pairs of numbers in the array. The function maxProductDifference begins by sorting the input array nums. Sorting allows us to directly access the two smallest and two largest numbers, which are required to compute the product difference. Specifically, the smallest numbers are located at indices 0 and 1 in the sorted array, while the largest numbers are at the last two indices, -1 and -2. After extracting these values, the function calculates the product difference using the formula, largest 1 * largest 2, smallest 1 * smallest 2. This formula ensures that the maximum product difference is computed efficiently. Finally, the result is returned. The algorithm has a time complexity of O(n) log n, due to the sorting operation, where n is the length of the input array. The space complexity is O(1), since no additional data structures are used beyond a few variables for intermediate computations. This is the Java implementation of the LeetCode problem number 1913, maximum product difference between two pairs. The logic matches the Python solution, where we first sort the input array. The two largest numbers are accessed from the end of the sorted array, and the two smallest numbers are accessed from the start. The product difference is then calculated. Differences include the use of Java's arrays.sort for sorting and explicit type declarations. Here, we're given the input array nums equals 5, 6, 2, 7, 4. The first step is to sort this array in ascending order, which gives us nums equals 2, 4, 5, 6, 7. Once sorted, we can easily identify the largest and smallest numbers. The two largest numbers are the last two elements of the sorted array, largest 1 equals 7 and largest 2 equals 6. Similarly, the two smallest numbers are the first two elements, smallest 1 equals 2 and smallest 2 equals 4. Now, we calculate the product of the two largest numbers, which is 7 * 6 equals 42, and the product of the two smallest numbers, which is 2 * 4 equals 8. Finally, we subtract these two products to find the product difference, 42 8 equals 34. So, the output for this example is 34. In this example, the input array is nums equals 1, 10, 3, 9, 5. we begin by sorting the array, resulting in nums equals 1, 3, 5, 9, 10. From this sorted array, the two largest numbers are the last two elements, largest 1 equals 10 and largest 2 equals 9. The two smallest numbers are the first two elements, smallest 1 equals 1 and smallest 2 equals 3. Next, we calculate the product of the two largest numbers, which is 10 * 9 equals 90, and the product of the two smallest numbers, which is 1 * 3 equals 3. Subtracting these two products gives us the product difference, 93 equals 87. Therefore, the output for this example is 87. Here, the input array is nums equals 4, 2, 9, 7, 8, 1. The first step is to sort the array, which results in nums equals 1, 2, 4, 7, 8, 9. From the sorted array, we can easily identify the two largest numbers as the last two elements, largest 1 equals 9 and largest 2 equals 8. Similarly, the two smallest numbers are the first two elements, smallest 1 equals 1 and smallest 2 equals 2. Now, we calculate the product of the two largest numbers, which is 9 * 8 equals 72, and the product of the two smallest numbers, which is 1 * 2 equals 2. Subtracting these two products gives us the product difference, 72, 2 equals 70. So, the output for this example is 70. The time complexity of the solution can be understood by breaking it into its key components. First, we have the sorting operation, which is done using Python's built-in sort method. This method uses timsort, an efficient sorting algorithm with a time complexity of n log n. Next, after the array is sorted, we access specific elements, the two largest and the two smallest values. Accessing an element by its index in a list is a constant time operation, O1, and since we do this 4 times, the total time for this step is still O1. Finally, the product difference is calculated using 2 multiplication operations and 1 subtraction. Each of these is also an O1 operation, so the total time for this calculation remains O1. These steps together help us analyze the time costs of individual operations in the algorithm. Now, when we combine all the steps, the dominating factor is the sorting operation, which takes n log n. The subsequent operations, including accessing elements and performing arithmetic, have constant time complexities of O1. Since n log n is the largest term, the total time complexity of the solution is n log n. Shifting our focus to space complexity, the input list nums is provided as an argument, and the algorithm operates on it directly. This means no extra space is allocated for the input. However, Python's built-in sorting method does require additional temporary space for its timsort implementation, which can take up to n in the worst case. Beyond that, we only use 4 integer variables to store intermediate values, which contributes a constant O1 space. Together, these factors help us understand the space requirements of the solution. When we combine all contributing factors, the space complexity of the solution is determined to be n, driven primarily by the temporary storage required for sorting. Since no other significant space is used, this remains the total space complexity. Now, let's compare this with a brute force approach. In a brute force method, we would iterate through all pairs of elements in the array to determine the two largest and two smallest pairs. This involves a nested loop, leading to a time complexity of n squared. The current optimized solution, on the other hand, avoids these nested iterations by leveraging sorting, which brings the time complexity down to n log n. This is a substantial improvement, especially for larger arrays, as sorting is much more efficient than iterating through all pairs. Space complexity remains n for both approaches because of the input array storage and sorting requirements. However, the brute force method might require additional space for intermediate results, whereas the optimized solution directly operates on the array without such overhead. Finally, analyzing the best, average, and worst case scenarios, we see that the sorting operation remains n log n in all cases. This is because Python's timsort does not skip the sorting process, even if the input is already sorted or in reverse order. The efficiency of timsort ensures stable performance regardless of the input distribution. Mathematically, the sorting step dominates the overall time complexity, as it scales with n log n, while all other operations are constant time and do not affect the total complexity. Similarly, the space complexity is driven by the sorting process, resulting in n. This makes the solution both time efficient and space efficient within the constraints given by the problem. When solving this problem, there are a few common mistakes to watch out for. First, many people attempt to sort the entire array every time they solve the problem. While sorting can work, it comes with a time complexity of log n, which is unnecessary here. Since we only need the two largest and two smallest numbers, a linear scan with n complexity is both faster and more efficient. Instead of sorting, you can perform a single traversal to identify these values. Another issue arises with incorrect pair selection. Some solutions mistakenly use the largest and smallest numbers to calculate the product difference, which leads to incorrect results. Remember, the task is to pair the two largest numbers for the maximum product and the two smallest numbers for the minimum product. Lastly, handling small arrays improperly can also be a pitfall. If the input array contains fewer than 4 elements, the problem constraints are violated, or the solution might fail. It's important to validate the input size to ensure it meets the minimum requirement of 4 elements before proceeding with your logic. Another common issue involves off-by-one errors when sorting the array. For instance, after sorting, some solutions mistakenly access the wrong indices, like using nums-2 instead of nums-1, which could lead to selecting the wrong numbers for the calculation. This can completely throw off your results, so it's crucial to double-check that your index references are correct after sorting. Additionally, in low-level languages like C++ or Java, integer overflow can be a problem. When multiplying two large integers, the result might exceed the storage capacity, causing incorrect results. Python handles large integers automatically, but in other languages, you may need to use long integer types or validate the number ranges beforehand to avoid overflow errors. These seemingly small mistakes can significantly impact the correctness of your solution, so addressing them is key. From an interview perspective, this problem is often used to evaluate your ability to optimize solutions. A key focus area is demonstrating that you can derive an O(n) solution through a linear scan instead of relying on sorting, which is less efficient. Be ready to discuss the trade-offs between these two approaches to showcase your understanding of algorithmic complexity. Additionally, consider edge cases carefully. For example, what happens if the array contains duplicate maximum or minimum values? Or if the array consists entirely of positive numbers, negative numbers, or a mix of both? These scenarios test the robustness of your solution. Lastly, when presenting your solution, highlight how a linear scan avoids the computational overhead of sorting, demonstrating both efficiency and clarity in your approach. This can leave a strong impression on the interviewer. If you're looking to deepen your understanding of this problem, exploring related problems can be very helpful. For instance, LeetCode 628, which focuses on finding the maximum product of three numbers, shares similar logic but requires you to consider one additional number in your calculations. LeetCode 1464 asks you to find the maximum product of two elements after subtracting one from each, offering another twist on product calculations in arrays. LeetCode 53, on the other hand, shifts the focus from products to sums, challenging you to find the maximum subarray sum, but it still requires careful array traversal and optimization. And of course, revisiting problem 1913 itself can help you practice variations or constraints, ensuring you fully understand the nuances of the problem. Working through these related problems will strengthen your problem-solving skills in array manipulation and product-based calculations. Finally, let's discuss some alternative approaches to solving this problem. The sorting approach is straightforward. You sort the array, then calculate the product difference using the two largest and two smallest numbers. While this is simple to implement, it has a time complexity of log n, making it less efficient. Another option is the heap approach, where you can use a max heap to find the two largest numbers and a min heap for the two smallest numbers. This is more memory intensive but still efficient, with a time complexity of log k, where k is the size of the heap, which in this case is 2. The most efficient solution is the single scan approach. Here, you traverse the array once to find the two largest and two smallest numbers. This approach has a time complexity of n and uses minimal memory, but it can be a bit trickier to implement correctly. Each approach has its trade-offs, so choose the one that best fits the constraints and requirements of the problem you're solving. Great job today! To summarize, we solved the problem by leveraging sorting to optimize finding the largest and smallest values in the array. Remember, this approach is both efficient and intuitive. Keep practicing, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!